This is part 3 of a universe in equilibrium. Today we're going to be talking about a new value for the universal mass. This is based on the Schwarzschild-de Broglie equilibrium. Okay, let's imagine that we're approaching the universe. And what we're approaching here is in an equilibrium. Now it's either in equilibrium with itself, its own internal quantum background, or its universal space-time, or it's somehow in equilibrium with pure and completely empty space, or with both. In order to persist, the universe must have an internal self-sustaining equilibrium, an internal quantum equilibrium through its own pure and empty space. Pure space is simply that which has no characteristic whatsoever. Space doesn't exist, and therefore it will sustain no equilibriums whatsoever. And therefore, the universe must have some kind of internal self-sustaining equilibrium that's maintained within its own quantum space through its own pure empty space. Pure space, however, does permit by injection through and into any locations within two equalized domains. What we really are dealing with is a determined quantum background that's in equilibrium with itself, this being the universe itself. This background is formed through by injected pure space, which has no characteristic whatsoever. Okay, so what we're doing is we're proposing an interaction that promotes space-time landscape through the graviton, and the graviton is the medium. So then this quantum space is an electromagnetic gravitational interaction location. And by location, I don't mean anything. It's just an interaction. This action has at its root the Planck interaction. And this is where quantum nucleation takes place. And this is where the holographic mass is generated. Okay, so now the inertial foci occur through the graviton envelope, such that essential moments, in the de Broglie and Schwarzschild radii are functionally contained in unique tensor field network relations. In other words, entangled localized tensor field network interactions are space-time. I want to make it clear that baryonic nucleation doesn't occur because of pure space. It occurs out of quantum space. Now, we can calculate the number of distinct Planck nucleation sites using the total universal energy and the Planck RMS energy value. Now, these nucleation sites are generating gravitons. So, these nucleation sites, which occur within the graviton envelope, are the source for gravitons. Okay. Now, taking as an example, dividing the proton mass or the proton energy by the graviton energy, we find that we have 3.2 times 10 to the 42nd graviton states within every proton. All right, so essentially 3.2 times 10 to the 42nd gravitons which are available for every proton. Okay, so we want to remember that these Planck interactions are extremely high energy and force equilibrium points that are very, very high energy, very, very closely spaced together. There are a lot of them in the universe. It works out to slightly more than the Planck length or the Planck interaction length. They're spaced almost one on top of the other and filling the whole universe. All right, and they are extremely high energy, very, very small, extremely small, the Great Gulf idea, and they support the whole universe through internal interactions. All right, and this, creating the baryons that we are experiencing, is evidenced by the E equals the Planck constant times the frequency. It's a local tensor field network interaction. It is simultaneously gravitational and electromagnetic in nature. Of course, what we experience is the electromagnetic side as a much stronger side because we're on this side of the interaction. Now, on the other side of the interaction, the much more reduced, extremely small side, that's where the actual gravitational interaction is taking place. So now what we have here is we've got simultaneous tensor field network entanglements, and they promote space through innumerous, really a lot of gravitons. That's 10 to the 123rd. You can see the calculation there. We arrive at the mass of the graviton. So this is Susskind's picture, and it's a very good representation of entanglement connection between two particles. And each connected point, represents the connection there represents a graviton that is in entanglement, between two particles, and that this entanglement is both gravitational and electromagnetic in nature. So remember that the graviton has an electromagnetic characteristic, which is the size of the whole universe, and yet has a gravitational characteristic, which only actually begins at the Planck interaction distance. The slides that we just got through, I explained the quantum background, what's actually happening. And now we're going to look at some of the macro events, and the actual full mass and energy of the universe. The universe is thought to be accelerating. This implies that there's some kind of force that's being applied. And now, what is that force? So taking Ernst Mach seriously, and we can determine that the universal constant G, big G, is actually the acceleration result that would be expected from a sum total of all of the available and equally distributed mass in the universe. We could conclude that the gravitational constant is proportional to the amount of mass in the universe, or the energy, as we have here. If we think about this, it's impossible to not come to the conclusion that all particles simultaneously share a split character. The character of each and every particle has a gravitational characteristic and also has an energy characteristic, as in electromagnetism. And these are separated by the velocity known as the speed of light. This implies more than one radius, a Schwarzschild radius and a de Broglie radius for each and every particle. And they derive from a single interaction. The radius is the Planck length times the square root of 2. And the reason for that is because that represents the root mean square value, power value, for the Planck energy. So we have then a transcendency for every point in the universe. The universe seeking equilibrium is actually seeking equilibrium between kinetic and gravitational energy. We find that there are specific temporary and local trajectories and accelerations. We find that there are local equilibriums that are achieved, And these achievements of local equilibrium lead to further adjustments at both greater and lesser magnitudes. And this seeking of equilibrium then continues. So the universe as a whole can be seen as being in multiple states, multiple phases that are in both partial and complete equilibriums. This conclusion is remarkable. It implies that there is a certain partial equilibrium that is already achieved. The universe is continuously seeking equilibrium. It is actively then seeking some quotient of further equilibrium. Now, the mass of the universe has often been cited to be approximately 10 to the 53rd kilograms, a finite number. Okay, and these approximations have been derived from critical density estimations, the average number of stars, including interstellar and intergalactic matter. Hoyle did a steady state estimate. And here on this chart, I have, the type of universe. We've got the WMAP total, the WMAP for all masses, WMAP in atoms, as measured just in atoms, the European Planck probe total, mass and energy, the Planck for all masses, the Planck probe for just for atoms, an average star, the mass of each star, the Hoyle total in atoms, atomic, and the Hoyle total. And then, finally, I have the equilibrium universe. We see that the mass, under the mass column, that all of them are pretty much in the same ballpark. And the equilibrium universe is the only universe whose Schwarzschild radius provides gravity its current value, okay, that at that radius you will get the black hole gravity value, which is the universal constant G. All of the other universes fall short of that. Either there's a lot more gravity or a lot less. There's a few that come close to it. The WMAP for all of the masses is roughly half the value of gravity, and the Planck value for all masses is also roughly half. Now, it turns out that the value for gravity being so accurately predicted with the equilibrium universe and the other values being so far off, it reminds me of the fine-tuning problem and the necessity of having universal constants that are very, very fine-tuned. This alone suggests that all of these other values for the universe are inadequate, and only the equilibrium model will answer to the question of fine-tuning. Now, just to explain just that little point about the natural radius, I calculate a radius where the gravitational acceleration at some radius would be equal to g. Turns out that we have the radius squared. Therefore, the radius squared for the Planck length times the square root of 2 would give us the mass of the graviton. Now, if we have a universal constant, g, we wanted to know what mass would be sufficient to produce a gravitational force. I call it the Schwarzschild force, that would be required to contain electromagnetic energy. Now, the universal mass, as I pointed out in the slide before and in the slide before that on the graph, this has been noted in many papers from Hawking to Susskind and others, and it's been overlooked that there's a constant involved here. It's a constant relationship. And it turns out that for our universe, the mass that is related to the certain radius is a unique solution, and the mass is 4.534 times 10 to the 53, and the radius is 6.733 times 10 to the 26 meters. And that will give us an equilibrium universe where the acceleration at that radius is equal to the universal acceleration of gravity. In this model, the universal radius resolves to its Schwarzschild radius. Now, I propose to show that given what we know about the quantum nature of our universe, this solution is necessary. It is the only solution that leads directly to the Planck interaction, to the Planck length, and to the Planck gravitational interaction as its convergent point. So, here are some of the things that this model performs. This equilibrium model leads directly to the Planck interaction as its convergent point. It directly points to the Bekenstein-Hawking constant. It confirms universal coherence, provides a logical and necessary source for Planck scale determinism. It informs quantum mechanics completely. It permits quantum mechanical and relativistic synthesis. And it predicts the total entropy and average universal density. And this I'll show in other videos. Now, the initial study included all types of particles from the electron through the equilibrium universe with the Milky Way, etc. And I've calculated the equilibrium universe force, which would be given at its Schwarzschild radius. And it turns out that for all masses, the Schwarzschild radius, if we calculate the force at that radius, well, it's a constant. Makes sense. But we see there is only one mass, and happens to be a total of mass, which confirms that the local gravity is equal to that Schwarzschild force, which is the necessary force to contain electromagnetic energy. Okay? That it's called the G parameter. It's also called the local de Broglie gravity, as what it calculates out to. And we have here the de Broglie radius, which we're going to be talking about later on for the equilibrium universe. The Schwarzschild radius we'll also be looking at as well. So go ahead and take a look at this. It's an interesting comparing studies. It's one of many studies that were done. And I hope that you find it interesting. If you have any questions, I'll be happy to explain any part of this. We will be talking a lot about imaginary and complex numbers, where the graviton becomes the universal conduit. Now, all of this implies trans-Planckian values, and this is a point that's been argued by many. And the solution is simple. It's instead of being considered as real numbers, we consider them as trans-Planckian. They are complex numbers. They are imaginary numbers. So we're proposing a mix of gravitational and electromagnetic domains, and that demands an accounting for both domains. And in space, we're going to find that transfers of energy in space, not pure space, but in quantum space, only occur by means of an internal medium. And that medium is itself the graviton, which is both part and integral to all existence and to all probability. Just to point out here how the Planck length times the square root of 2 lies at the center of the universe. I have here, under descriptions here in this little chart here, 1/2 of the Planck mass. We have the Planck mass, and we have the equilibrium universe. Okay, gives us a Schwarzschild radius of 6.733 times 10 to the 26, and a de Broglie radius of 7.759 times 10 to the negative 97. And we're going to be using these two numbers, so just be aware that I've noted them out for you here. Now, how does this Planck interaction lie at the center of the equilibrium universe? We find that 2 Planck lengths squared. Take the square root of that, will give us the Schwarzschild RMS Planck value of the Planck mass. And at this point, the Schwarzschild radius of 6.733 times 10 to the 26 and a de Broglie radius of 7.759 times 10 to the negative 97 are equal only for the RMS Planck value. Any mass energy values will always give the same result, and it will always give us this RMS Planck value. Okay? This is significant. Now, how does this Planck interaction lie at the center of the equilibrium universe? Well, if we take reciprocals, multiplying them by each other, it gives us the value of 1. Once again, we're using the RMS value of the Planck energy or the Planck mass. This Planck interaction is the source, that same RMS value, turns out to be the exact source of the Bekenstein-Hawking black hole constant. We can go ahead and look that up. So we have the Schwarzschild radius and the de Broglie radius, okay, for any and all particle masses. It's universal and it confirms that all things have their source in the Planck interaction. The equilibrium universe is the unique model that indicates these values. So, if we look at the effects of special relativity and general gravitational relativity, how do they fit into this universal equilibrium? Now, here I have a proton under the description, and you can see the proton at rest and going up and approaching the speed of light. So, the mass of the proton at rest, 1.6726 exponent 27. And you can see that it increases as we get closer to the speed of light. No real increase until you get very close to the speed of light. And there it begins to jump, such that the time dilation also begins to shrink. It shrinks because the de Broglie frequency is becoming higher, requires less time for light to transverse. So this is a first indication of how the Planck interaction is going to begin to shape reality as we know it. To the next slide. As our particle begins to approach the Planck mass, it begins to experience gravitational time dilation, and that's pointed out here. You can see that the time period for the Planck mass, okay, and the de Broglie wavelength for the Planck mass. Now, notice the Schwarzschild radius at rest for the Planck mass, how that's 3.232, okay, which is that same number that's coming up. Now, for the half Planck mass, that same de Broglie radius, which is a Schwarzschild radius for the Planck mass. So, any proximity that it has, and as it's approaching a Planck mass, it's becoming closer and closer. Now, for the Schwarzschild radius of a RMS value of the Planck mass, we have 2.285 times 10 to the negative 35th. Now, we find that exactly here for the 0.707 Planck mass. And note that de Broglie radius is equal to the Schwarzschild radius. So at that point, it's gone. So a little bit further on this trans-Planckian problem, and is it really resolved? And we see that after becoming a Planckian black hole, at half the Planck mass, all measurements and solutions are already complex or imaginary. Now, arrow number 1 and that column and that whole column shows the Planck-Schwarzschild radius. All right, we're going to be comparing things to that radius. Arrow number 2 points to the de Broglie radius for the RMS Planck mass, and you see that a lesser Planck mass already has a de Broglie radius, which is within the Planck-Schwarzschild radius. Now, so as it's approaching a Planck mass, it will find itself already becoming part of a black hole. Now, arrow number 3 points at the period, the Planck time. Now, in order to derive the values of number 4 and number 5, which are dilated time values, I used a comparison of the Planck-Schwarzschild radius, column 2, for all of these values. And I use it in comparison with the de Broglie radius, okay, for each of those same mass values. And you can see that the 3.232 from arrow number 1 and the 3.232 from the half Planck mass value are equal, and they give a dilated time which is 0. Now, as we go onward, going anywhere past that, we immediately go into complex numbers. And that would be the RMS Planck value, which is intermediate value between the full Planck mass and the half Planck mass. So what we see is that the Planck mass is the highest mass available in space-time for any particle. Now, groups of particles, conglomerations of particles, that's a whole different story because you have particles acting separately, but you do have this limit, and the limit divides mass on a particle level from mass we call normal mass, and we begin to see the differences. And it's a very, very small mass even still. For arrow number 4, we have for half of the Planck mass that we are already to the Planckian black hole. And as we move up to the RMS Planck value, it becomes a complex number at that point. All right? So this Planck mass is an imaginary complex solution. That is the description for the universe in equilibrium. The new mass value comes from that same model, and it's a better explanation. And one of our next videos is going to be on the graviton. And the videos are not going to be coming out all in order, but I hope you stay with us, and thank you for listening.